So, a hearty good morning to all of you, and very heartily welcome to all of you to the MIDAS expert webinars. So, today our topic will be numerical analysis of tailings dam. My name is Chinmay, and I work as a senior geotechnical engineer in MIDAS IT India, and I'll be your host for the session. So, this session is mainly intended to demonstrate the methodology of simulating the design and stability of a tailings dam, so we can predict and analyze on-site behavior or any approximations for advanced warnings. So construction techniques, some brief ideas about tailings dams and workflow process of finite element modeling along with output results and monitoring will be discussed. Now, coming to the agenda for today, we'll start with introduction where I'll talk a brief about tailings dams. I'll cover one infamous disaster from Hungary. Then we'll talk about some of the design considerations. On the second part, we'll come to the numerical model. I'll show you the section drawing, the ground parameters, materials and calibration, meshing and loading conditions, and the boundary conditions. Finally, in the analysis and output part, we will show you the construction stages planning, the results of FEM, and the results and output tools. Then we'll show you the factor of safety charts. Then we'll take you to the numerical model. So I hope everyone is clear with the agenda for today. So we will start with the introduction part. So what is a tailings dam or how does it look like? Some of you might be new to the section. That is why we have decided to give you a brief intro about these tailings or mine waste storage facilities. So tailings dams or tailings impoundment facilities can be seen on the left side of the picture. So here you can see there is a mine and then there are processing facilities. As the ore cannot directly be used as the grade for the smelter, that is why we sent them to beneficiation plants where the ore is mixed with various compounds and then they are sent to the smelters. While some of the waste that accumulates, they had to be stored somewhere. And these wastes normally contain very heavy metals. That is why they have to be stored somewhere. So these toxic or sometimes radioactive elements have to be stored in dams. These dams are called as tailings dams. So to summarize, they are nothing but dams to store the mine process waste, and they have very high chance of liquefaction because tailings are fine silt, sanded silt particles, so they are very prone to liquefaction. They are built to store the waste until the next ice age, or they can also be called as build and forget dams. And unfortunately, the mining companies they don't make any money from it. That is why sometimes these dams fail. So, in terms of regulatory agencies, there are ANCOLD from Australia, the Directorate General of Mine Safety from India, and Groove Redas from Sweden. So, one infamous tailings disaster is this. This is actually a picture from Hungary. Unfortunately, no place in the world is safe from dams disasters. So, this started when a section of the corner completely gave away. This is a red mud pond or bauxite storage tailings facility. That is why it is red in color. And once the unfortunate corner gave away, the entire slurry flew, and you can see the results of the post failure. So, if a dam like this fails, this area is rendered worthless for both flora and fauna for a very long time. That is why extreme care should be taken that these dams should never fail. So, in terms of design considerations, we have to also take economics into account along with the choice of the storage area or how much containment has to be done. That is why the first thing is to ensure that you select a size where you can reduce the catchment area. Also, we have to maintain a wide beach control to check the internal storage, because there will always be seepage from the pond. Then the starter dike is first constructed, and then the segments are built on top. Also, the starter dike act as a good place for drainage. We will come to that on later stages. Then we have to also exploit the previous foundation conditions, which essentially means if there is a hillock nearby which can be used as a demineralized zone, we can build a tailings facility in there, because it will reduce the amount of material needed for the construction of the dam. So, coming to the choice of impoundment area, there are basically three types of impoundments. Existing open pit impoundment, where the existing open pit is used for dumping the tailings and storing it. Example is a copper mine in Arizona, US. Then there is a ring dike or a cell impoundment. These tend to be the most expensive impoundments, because you have to build the dikes all around. That is why the amount of material it goes up, and also one can say these are the more susceptible dams to fail, because the more the more filling of materials on a even terrain, the more chances are that the dam might fail. So these corners, they are the most dangerous spaces for the dams to fail, because of accumulation of tensile stresses or low effective stresses. Now, the third is the valley impoundment. These are the second cheapest after the existing open pit impoundment, because here you take advantage of the walls of the hillock, or let's say hill, and you just need to create a big barrier to store the facilities in there. So finally, coming to the three type of construction methods of tailings dams. Now, there are three types of methods. These are the upstream, downstream, and central line. Upstream method is the cheapest method. So starter dike is created, and then subsequently the raisings are created which rest on the previous raising as well as on the tailings. The advantage of this method is that it is the cheapest method to build the tailings facilities. Also, the fact that they require much lesser material than other methods that can be illustrated in the diagram right away. But on the hindsight, they are the ones that fail the most, because of chances of liquefaction for high pore pressures or seismic incident. Any area that is prone to a seismic zone, you cannot build upstream dam in there. It will fail for sure. So that is the unfortunate issue with the upstream method. The downstream method means the starter dike is created, then the subsequent reagings are created on the downstream side. Out of the three methods, it is the most safest method. At the same time, it is the most expensive method too. That is why an improvisation called as the center line method had been brought into practice. So here you have a upstream and a downstream construction, which essentially requires that you need lesser material than the downstream method, but still you need more material than the upstream method. But on the good part, this dam is much more stable than an upstream construction dams. So with that being clear, let's come to the numerical model. So for the cross-section view, this is the tailings dam, or these are the tailings storage, the foundation, the bedrock, the core. Then we have the rock fill on the upstream side. Then we have a coarse and fine filter on the downstream side, a buttress or a rock fill support. Then we have the raising cores. Each raising core is of 6 meter height, and the rock fill protection or the rock berm is of 2 meters. Okay, and these tailings, they depend on the size of the raising itself. At first, the three deposition are of around 12 to 12.5 meters to max 15 meters height, one, two. Then the rest of the deposition are of 6 meter height. So these 6 meter height deposition, they coincide with the fact that each raising core is of 6 meters. So one has to understand the dam can only be built after the deposition has been done, and then we apply a water cover to it, or In terms of FEM numerical modeling, we call it as a nodal head. Next, coming to the hydraulic properties. So here we have a core, a foundation, the deposited tailings, the fine filter, coarse filter, and rock fill. The core is made of glacial till, so is the foundation soil. So for the core, the Kx and Ky are nothing but the permeability in x and y direction. That is the horizontal permeabilities. Kz is the vertical permeability. So based on the book called as Geotechnical Engineering of Dams by Foster and Fell. So anyone who is kind of new to the dams industry and they want to focus or know more about dams, we will highly recommend you please download or you can buy the book. You can always read everything about dams in there. All the details that have been provided here comes from that book itself. It's like the encyclopedia of dams engineering. So according to that book, when soil is deposited in a stratified layer and then compacted, the permeability can change from a margin of maximum 15 times the original one. So here, based on that, we have taken a factor of 3 or 4 times from the original permeability. That means the horizontal permeability is equal to 3 times the vertical permeability. So these are the material parameters for the core, ranging from the core to the rock fill. Next, coming to the geotechnical stiffness parameters, we are dealing with a more column model here. That is why we only need 5 parameters: unit weight, Poisson's ratio, E modulus, C, and phi. That is the friction angle. So for the core, the C value is 5 and the friction value 26. For foundation, C value is 5, friction angle value is 32. For the deposited tailings, they are actually quite weak. So the C value is 1 and phi value is 22. Fine filter and rock coarse filter are made from sand and gravel. So they have quite low phi value too. And finally, coming to rockfill, we are looking at a friction angle of 38 degrees because they will provide the buttress support. So I hope the material parameters were easy for you to understand. Next, we'll define the workflow process. So any FEM model, be it in any software, regardless if it is GTSNX or Plexus or GeoStudio or any other software, the workflow process more or less remain the same. That means the geometry, then the materials, then the properties or the element attribute. When you say property, that means that you are converting the material from a physical property to a finite element property. Okay. Then the mesh, then the loading and boundary conditions. That means for any static load or dynamic load, or in our case in here, that is will be self weight or static load along with the chance of the seepage boundaries. Then finally the analysis, and in the end the results. The steps 1, 2, 3, they can be interchanged. Like you can always define the material property before creating a geometry. So but from the part 4 it cannot change. So 4, 5, 6, 7 will remain constant. 1, 2 can be interchanged with each other depending on how you feel comfortable. But for me, I generally start with the geometric case. So I start with the geometry, then to material property, and henceforth. So coming to meshing, this is how our mesh will look like. The left part of the mesh you are seeing, they are the tailings deposited. I have deliberately kept them as transparent so that I can focus more on the cores and the starter dikes. So here you can see we have a quad shift element. So on a 2D section view, it looks like a quad element, but in a finite element methodology, it will be called as a hexahedral element. So hexahedral element means they are based on summation of tetrahedral elements, which means we have 6 nodes. The more number of nodes we have, the better the clarity of the results. But here again, you can see in some sections you can't have a hexahedral element. So the software decides where it cannot have a hexahedral element. In those places, especially the corners or the edges, is where you will find a tetrahedral element, so that the mesh can be uniform. In a finite element mesh, the mesh has to be uniform and continuous. If it is not uniform and continuous, there is a mesh failure, then you cannot come to a result. That is why the software automatically assigns a tetrahedral mesh at some parts. Example here, or in the corner like here. Okay. Next will be the boundary conditions. So here we have two boundary conditions. One is the ground boundary condition, which essentially means that sides will be on roller supports and the bottom will be on fixed supports. That means the model is allowed to move on sides, but not on the bottom. Otherwise, the model will completely collapse under its own weight. That is why we have a fixed boundary on the bottom. So now coming to the seepage boundary conditions. So we have two CPS boundary condition, that is the nodal head and the review boundary. The nodal head is nothing but the water pressure or the water head that we give for seepage, and the review means the potential seepage phase where the seepage will take place. So next we will define the construction stages and go towards the analysis. So I'll play a small animation of the construction stages, then I'll define you what it exactly looks like. So you can see with each deposition, the reagings have been done along with the rockfill support. And after this sixth raging, we start creating the butters so as to ensure that we can check on the factor of safety, or we need to stabilize the dikes. Again, this is a preliminary design. That is why we have not done a comprehensive check for this, because at first we need to assess what exactly are we looking getting ourselves into. So based on that only we can make a calculated judgment, or one can say it is a pre-feasibility design for this particular tailings storage facility. Clear? So next we'll come to the results and displacements. So this is how the horizontal displacement looks like. That means it is entirely trying to push the slope outside, which essentially reduces the effective stresses on the outskirts or on the edges of the model. And normally this is also the same case in dams. Due to lack of confinement, we experience small local failures. So our job is to ensure that these small local failures remain small, they don't become big, which is why we do a numerical mode. So in total head variation, here the total head varies like this, from 100 to around 0. Then the pore pressures, they look like this. With each raising, you can see the phreatic line on top. So next, we'll come to the slope factor of safety results. So the slope essentially starts with a factor of safety of 2.2 on the first deposition, then 2.4, 2.2, 2.1, 1.9. In the seventh raising is where we start to breach the guideline value of 1.5. 1.5 is the guideline value in most of the dam safety codes all over the world. It might be a different in some countries, but again, we are not extremely aware of it. So we will limit our scope to 1.5 only. Anything below 1.5 for a normal operating procedure is not safe. That means after the seventh raising has been done, the dam is not safe anymore. So which means that we need more more support systems. But again, if we go back a few minutes back, I had clearly mentioned that this was a pre-feasibility report. That is why we needed to check what exactly we are looking for. So we understand the amount of rockfill we have put in there is not enough, and after seventh raising, the factor of safety will go down. So in the second part of this webinar series, that will come probably a month or two from now, we will show you the more comprehensive uh, design of what we exactly did for this model or for this project. So now you have checked the displacements, you have checked the pore pressures and the factor of safety. So these dams are built for, as I mentioned, for the next ice age. So the question is, how do you monitor it? A lot of you are aware of extensometer readings or inclinometer readings, but nowadays there is a new type of monitoring equipment, that is the InSAR modeling. So the InSAR results look like this. So this is also a tailings dam. This is actually the tailings dam of Aitik mine in Alevar, Sweden. That is in northern part of Sweden. The operator is Boliden. So they do this InSAR modeling, and also this InSAR modeling on monitoring is quite becoming more and more common for other mine sites all over the world. So this is a good way of checking every year that what kind of deformations the dam is taking place. So this is also a non-destructive method. So it is, you don't need to install anything anywhere, and you don't have to be uh, very much careful about your data getting lost or your equipment malfunctioning, because we have enough satellites to cover these studies. So in the next slide, I'll show you a bit more details about the particular monitoring system. So with the sensor monitoring, what they have done is they have taken 2 points, and based on each date along the line of sight, they have monitored the displacements in year. That is point one and the point two. These two graphs on the right, they show the displacements in based on each date. So if we start with the top right graph, you can see, and again these are data interpretations, so there is a chance that it might be a bit wrong based on the interpretation of the data. So that is what the operator has to check, like what is the clarity of the data that we are getting. So I hope everyone enjoyed the presentation. Now we will go to the numerical model. Okay. I hope everyone enjoyed the first part of the session. So before we jump into the second part, there was something I have talked about drains on the starter dike. So I'll just show you the concept of what happens when you have a drain and what happens when you don't have a drain. And also that is a very conclusive way of noticing that how seepage might work for a very big dam or a very big storage facility. So I'll start with this. So I hope my screen is visible to all of you. So this is a starter dike, and here with the tailing storage, this facility has some drains connected in the rockfill right away. These drains can lead into the foundation, or they can also lead into the starter dike. In our numerical model that I'm going to show you, there we lead the seepage water into the starter dike, and that's from where it goes out. So the question is, what happens when you do not have a drain? So these are the results. I'll show you three scenarios, and one of them is a safe scenario, two are very, very unsafe scenarios. So I'll let you notice that. So this is the first scenario. So this scenario is not a safe scenario. Why? Because the phreatic line is going inside the raising course, and you can see the vertical drop in some places. So by the time the line reaches here or the starter dike, it is the water pressure can be very high due to the drop in this hydraulic gradient, which is not a smooth one. It is a very harsh one. So you can expect chances of internal erosion in this raising, and also somewhere in this part, which you absolutely do not want. And these things or these results are only predictable by using numerical modeling. It is otherwise very hard to predict by hand calculations. And this is what we call as a safe scenario. Why? Because you can see the phreatic line crosses through the drain in here. So we had designed the drain in this part, and the phreatic line from top drops and goes through the starter dike and goes out via the buttress, where it can be collected in a decant pond or a collection pond. So coming to the third part, the first part was where where we saw that there is a chance of internal erosion in here in the raisings, or maybe in the starter dike in the future. The second part, we show a safe scenario where the phreatic line stays away from the consolidation or the high strength zone. Then the third part, that is the most dangerous part. I'll just let you look at the picture and do let me know your thoughts on the questions panel. So do you think this is actually a safe scenario for the phreatic line to drop like this? The answer is obviously no. We would never want the phreatic line to drop here because the water pressure will be extremely high near the toe, which can lead to erosion first. Second, it can lead to sinkhole formation when the water actually blows up in the downstream side. So by using numerical modeling, it was actually predictable that what kind of drains we need to design to ensure our dam remains safe throughout its lifetime procedure. Yes, one can say that the filter or the drain might get choked. Then what is going to happen if this drain somehow gets choked? Then this might happen or this might happen. That is why we cannot let our drain choke. So I hope this concept of phreatic lines or drainage systems was clear for all of you. Now we will go to the numerical modeling part or the second part of the session. Okay. So if you have any questions regarding the seepage design that I showed, you can feel free to ask them on the questions panel. I'll answer them to the best of my abilities.
On the GoToWebinar control panel to allow all attendees to hear you. This system will notify you once you begin your broadcast. The broadcast is now starting. All attendees are in listen-only mode.
So this is the collection of the tailings dam model that I had talked before. So you can always draw this entire cross section here, but I'll recommend if you already have your CAD drawing, just import them right away. It is far easier than that, rather than drawing the entire thing from scratch. So you can also import data from your DEM model if you want. So here you just go to make face, go to grid face. You can enter your DEM or digital elevation model data in here and create your complete ground topography. But again, here we are not focused on that. So here, since we already have the main drawing with us, so we don't need any DEM data. So we will start by creating faces. Right now, what we have is 1D drawing. So from here, we need to go to 2D, that is by creating faces, then from 2D to 3D. Okay, so I'll just show you an example. I'll go to geometry, make face, select the curves like this, and I press apply. Okay, so this is how you can create your faces, and to extrude them into 3D, just go to isometric view and go to protrude, select this direction Y, your desired length. You can see it's one of the preview option looks like this. So let's say you have a curved surface, like let's say you are trying to model the corner of the dam. So what to do in that case? So let's say you have your surface like this and you have a curvature. So what I'm going to do is I'm just going to create an imaginary arc that will form the basis of my curvature. So I'll go to 3D, select 3 point arc system. First point in origin, second point let's say somewhere in here, and then third point let's say in here. So this is my arc. Okay, so to extrude that into the arc form, what I need to do is go to my target object, guide, I'll select edge, and then you can see this is how my curvature will look like. Okay, so now coming back to the main section. So once you have created all your faces, is going to look like this. So this has to have a bit more clarity. You can select all, click right click, press on random color. So now you know everything has been separated from each other. So to create a 3D model, all you need to do is go to extrude, select all faces, direction, y-axis, length 100 or 150 meter, whatever you desire. So that's how you can have your 3D. So after this, you just go to the solids right away. So these are the solids which essentially are of 100 meter cross section length. Okay, these are the deposition areas, pores, rock fills, extra rock support buttress, the main dam or the shattered dike foundation. So when you go to meshing, as I said, you have the choice of two type of mesh sets. So the tetrahedral or the hexahedral mesh. So we'll pick the hybrid mesher, and based on that, we will apply the meshing conditions in here. I'll select the foundation. Okay, size 5. So if I click on the preview option, you can see you get the nodes in everywhere. If I put a size, so 10, so this is how the nodes will look like. So one can have a question like what mesh size should we use? So the mesh size is actually dictated by the size of your element or your object. If the object is very big, you cannot have a very fine mesh. At the same time, if the object is very small, you cannot have a big mesh. So this is something, it completely depends on the user what kind of mesh size you want to dedicate to it. So here I'll show you what meshing that I had given. If I go to basic mesh set, foundation, I had given it a mesh size of 10 units or 10 meters. That means each node is located 10 meter apart from each other. One, okay. So if I look at here, one, around 10 meters. See, it cannot be exactly 10 meter, it can also vary. Here in the beginning, you saw it was 4 meter because here is where the ground or the foundation mesh meets the core. The core has a mesh size of 4 meter. So that is why in the periphery where the two mesh sets meet, the size of the smaller mesh will be taken into account because in order to maintain the uniformity. So the mesh will look like this. So to apply the boundary conditions for the seepage boundaries, what I can do is just go to nodal head. So let's say here in I have shown that it was 82.5 meters maximum head. So here I want to give the 82.5 meter head. So what I do is select all the nodes from the top like this. Okay. Then I give it a value of 81.5 meters, 825 head. Okay, it's gonna look like this. Similarly, for each section, you can give it a nodal head like this. Otherwise, there is even a simpler method for doing this. So instead of picking up mesh, you can just apply them directly to the solid face. Go to object face, same thing. Okay, head one. So this is far easier to apply than the mesh sets. So both ways will work for you. It depends on what or how you want to deliver it. So we have to give it the nodal heads, not the water level, because we are doing a coupled analysis, that is CPS plus slope coupled. That is why we need the nodal head and also the review boundary or in some other softwares they are called as potential CPS phase. So again I select phase. Okay. So the entire downstream phase is my CPS phase. So you can always press apply after that or okay. One gonna look like this. So these are the two boundary conditions for the seepage boundary. So each height of deposition will be succeeded by the same height of the water level in order to maintain the actual flow of water or to simulate the ground conditions as much as possible. So here what else we had done was that we applied a drainage condition in the rock fill. Some tailings dams have this drainage condition for the rock fill, which we apply in this part. So if I just activate all the mesh and switch off this one, I'll show you what is the advantage of that. So here what we do is we just give a zero head boundary, okay, and to select we just click on the rectangular option and select these lines as a drainage so that we are ensuring that the drainage is facilitated in this region, so the pore pressures will not be high inside these pores or under these pores, because these place areas are called as the strength zones or the consolidation zones, which means these are the places which will take the maximum loading imposed by each of the raising pore. The higher the pore pressure in this area, the more uh, the dam is susceptible to failure. That is why we need to ensure that these areas are remaining free from high pore pressures. Which is why sometimes in some dams, we what they do is they apply a drainage zone in here. Okay. So after that, what we do is we just assign this ground boundary conditions. Go to constraint, go to auto, name it as. So you can see fixed support on the bottoms, rolling supports on the sides. So after this is done, what we do is we go and create our analysis cases. So we go to stage set. So here, this is how it looks like. So we started the entire model because we are more focused on the downstream only. So here, what we did was the first layer of deposition with a 12.5 meter head. Then that layer is succeeded by a stress stage, where we see the change in the ground stress condition because of the water loading imposed and also because uh, of the weight of the tailings on the upstream. Next will be the 22.5 meter tailings and then the same head, okay, and so on. So the third deposition of tailings is succeeded by the creation of the first core. Again, I need to remind you that we have taken only more column materials for this one. We have not taken consolidation or hardening soil into account. But yes, hardening soil can be used for this particular methodology. It it might give you some more accurate results, but we have not done that in here, so I'll decline to comment on that. And then we proceed with the nodal heads and then stress, nodal head and stress. You can see from the seventh raising, sorry, from the fifth raising, you can see the buttress is activated. So from the graph that I shown in the presentation, we know that this rockfill was not accurate. But what we have done is we have designed the rockfill in the same manner or with the same exact slope angle as the uh, original dikes so that the construction is easier and also there is free space remaining in here. That means the rockfill height can be raised from here. If that is still not enough, we can always widen the rockfill on this direction for incremental support during the later stage of the dam. So here we will get results from three kind of analysis: seepage, nonlinear static, and SRM. SRM is strength reduction method or the finite element method for factor of safety calculation. So right now we know the factor of safety results. So what we'll do is we'll go to the results right now. So for the first deposition stage, the phreatic line, the total head, okay. Then here you can get everything else like flow velocity, which will come to a bit later on. Then the displacements, horizontal displacements, okay, vertical displacements, the stresses. The S-axis is the total stress, then the effective stress in the horizontal direction, effective stress in the vertical direction. Pore pressure. Here we do not have any untrained parameters, so we are not taking into account any excess pore pressure. Plasticity status. Similarly, if we come on to the middle stage, let's say the seventh raising, you can see, remember we designed a drainage line in here. So you can see it works wonderfully. This is a good phreatic line. Like this is a phreatic line we can all accept. If the phreatic line drops suddenly, then you do not want something like that because that will eventually lead to blowout or excessive seepage. So phreatic line dropping like this is a good indication. Then the degree of saturation will show you how much exactly the phreatic line actually lies. So on top of the phreatic line, this will be unsaturated zone. Below it will be saturated zone. Here we have not taken the unsaturated properties into account. That is why we are assuming it is completely saturated in the bottom. So based on that, the total translation. So you can see the tailings are being loaded with weight of the water and weight of the dam of the raising course. So they will experience the highest deformation. So here, a bit far away from the dam, what happens, we are not very much concerned with it. But what we are concerned is what happens in this zone or the zone where there is low confinement. So there, if we want to see the results right away, you can also create a probe or a boundary query and just select certain points. Okay, so these points show me the exact displacement in centimeters. So I just zoom it in. You can see they look like this. Okay. So similarly, if I come to let's say the 12th stage of raising, the phreatic line, again our drain works wonderfully. then the degree of saturation. What we also have in here is the resultant flow velocity. So there you have it, the flow velocity. They go to the value maximum flow velocity here is 0.89 centimeter per second, and that is through this region. This means this will be the area where we will need to look for reinforcements in the future from here and also from here. So 0.9 centimeter per second means this dam is not exactly susceptible to internal erosion. But again, that is also a very long-term topic. So we cannot exactly guarantee that okay, this is not susceptible to internal erosion in the long term, because things change when something is being operated for 50 years or 100 years, or let's say more. But as of now, from the preliminary design, yes, we can conclude that because the this velocity is virtually nothing. 0.9 centimeter per second is very low for that. And also we have a control on the phreatic line like this. If the phreatic line would have dropped something like this, then it would have been a problem. But for this picture, no. I mean, not enough, not in full area of concern. Finally, in the last stage, the degree of saturation looks like this. The displacements, you can see. So here you can see that why we need constant monitoring, because towards the end stages or the stages when the dam is almost fully built, the deformation will become very high. So that is why we need the InSAR monitoring or extensometer monitoring, depending on the available budget of the client. So now finally coming to the stresses. So I just change unit to kilonewton per to kPa. Total stress on the edges. You can see on these edges we don't want very high tensile stresses, because that means it will collapse. So compressive stresses are negative, tensile are positive. So look for the effective stresses. They are on the negative zone. This positive 15 kPa, so this might become a concern area in the vertical stresses. Then the minor principal stress. The vectors will show you the direction of the minor principal stress like this. The major principal stress, then the mean effective stress. The mean effective stress will always be on positive. Then the plasticity, like this. So finally, we come to the factor of safety results. Actually, I created two models for this. I ran them side by side, because again SRM is an iteration method, so it takes some time to get the results. So for factor of safety, like we seen in the chart, you can see the variation of factor of safety. So for the final raising, this is how this slip surface looks like. So if I keep on going to medium stages, they look like this. Okay, the slip surface area. So let's say I want to see the factor of safety in the ninth raising. So this is my critical slip. Then the horizontal displacement will look like this. So one can see the SRM results are very high. So if you have a doubt, then please don't worry, because SRM results what you get on the screen are just before the failure. That means the model will fail with this amount of displacement. So for static conditions and CPS conditions, these are the results you can get. Okay. So and you can also do a liquefaction analysis in GTS. For that, you need to create this create your properties in nor sand model, okay, or PM for sand model, depending on what you feel comfortable with. So I hope for now this is all I had to show for this particular presentation. Also, if you have any suggestions on improvement or anything that you want us to showcase, you can always, let us know at geotech@midasit.com. But for the session currently, for any questions, please feel free to note them on the questions panel.